Hi, welcome to your lesson on mutually exclusive events, and part 2 in this video will be about sample space diagrams. Okay, let's begin with inclusive versus mutually exclusive events. So a recap of some formulas we've seen and the idea of inclusive and exclusive events. So inclusive events look like this. There's an overlap between events. That means both things can occur at the same time. In this case, when we have A or B, the probability of A or B, or always means union, so A union B. And if you remember, that means everything in this circle and everything in this circle. So the union is everything represented with both circles shaded, including the overlapping zone in the middle. And that formula was probability of circle A plus probability of B minus the intersection. And again, we're subtracting the intersection because if you add this circle plus this circle, you're counting that part twice. So we're going to subtract that intersection once to just capture everything that's in both. And our A and B, which means the intersection, can be calculated by taking the same formula and just moving this to that side and that to that side. So switching the location of the union and intersection in the formula through algebra. Okay, we've looked at those before. Let's recap also mutually exclusive events, which are also called disjoint, and they look like this. Now there's events that have no overlap. That means both things cannot occur at the same time. Our A or B formula, or our probability of A union B, well, do these have a union? Yes, we still look at for union as meaning everything in here and here. So probability of A plus probability of B. And notice here we are not subtracting intersection because there is no intersection. So to find the union, we just add up everything in there plus everything in there. For our intersection formula here, so A and B, well, the intersection of A and B is 0. The probability of there being an intersection here is 0 because they do not overlap. So both things cannot occur at the same time, so their probability is 0. So that's just a recap of something we saw in the last lesson, but these formulas are important throughout all of probability, and we're going to use them again right here. So the first problem we'll look at is this. Arthur has a drawer which contains ties. He picks a tie at random from the drawer. The probability that the tie is blue is 5/12, and the probability it is red is 1/3. And we are told that 2 of the ties are bow ties, 1 red, 1 black. Another important note here is that each tie is just one color. So this picture shows ties maybe with a couple colors, but imagine in this problem, all these red and blue, the red ties are only red, the blue ties are only blue, this black bow tie is only black, and so on. Okay, so the 2 questions are these. Please try question 1 to begin. Okay, let's take a look at how 1 can be looked at. So what is the probability he selects a red tie or a bow tie? So first thing to determine when you have an or problem is, are they inclusive or are they mutually exclusive? Because if they're inclusive, if there's an overlap, we have to use that longer formula, subtracting the intersection. So are these inclusive? Well, they are, because a tie can be a red tie and a bow tie, right? Because we have 1 red bow tie, it told us here. So this is a situation with inclusive events because a tie can be both red and a bow tie. So we have to then use this formula because for overlapping events, we need to use the full formula where we subtract the overlap. So red or bow tie equals probability of red plus probability of bow tie minus the intersection, the red and bow tie. So here's what our closet might look like. We have 5 out of 12, here's 12 ties, 5 of them are blue. And then it says probabilities red is 1/3. Well, those don't have the same denominator, but we can change that 3 to a 12 by multiplying by 4 and multiply this by 4. That means 4 out of 12 ties are red. So here's our 4 red out of 12. And we know one of the red ones is a bow tie, so I put in a bow tie here. And that leaves, well, here's 5, here's 4. That leaves 3 more ties out of 12 that are neither red nor blue. But one of those is a black bow tie, so here it is. So that's an image of what we have here. So what's the probability he selects a red or bow tie? Well, red or bow tie, we have 4 reds, 2 bow ties, subtract the intersection, the red bow tie, and we're left with 5 out of 12. So hopefully you're able to come up with that answer. Let's look at a Venn diagram to represent the same thing. Here is our universal set, 12 ties. Here are our 4 red ties. Here are our 2 bow ties. And in the middle here, we have the red bow tie. So there's the inclusive part, the intersecting event, the red bow tie. And if that's a 1 and this is a 4, this must be a 3 because that makes 4 in total. And if this is a 2 here and this is a 1 here, this must be a 1. So that's the one remaining bow tie, which is this one. And that means a union, red or bow tie. Union is everything in these circles. And we can see those numbers add up to 5. Also, these numbers don't look like 3, 1, and 1 here, right? That's because we took all 4 of these plus both of those, which makes 6, and then subtracted away that, which gives us the 5. So that's how all that connects here. Let's look at this question. What is the probability of Arthur picking out a tie that is neither red nor blue? Okay, so let's see what you came up with. Neither red nor blue. Sometimes with these ones where it's neither, it's easier to begin with, well, what's the chance it is red or blue? And then you take that away from 1, because you have 1 is all the possibilities minus red or blue, and you're left with the ones that are neither red or blue. But first of all, these are mutually exclusive, because a tie cannot be red and blue at the same time. So imagine that as a Venn diagram with red circle, blue circle, but no overlap. Okay, so if there's no overlap, we're going to use the mutually exclusive formula for union. Okay, and we're going to say, what's the probability of getting a red or a blue? So it's just probability of red plus probability of blue, no subtraction. And those numbers are 4 reds plus 5 blues. So we have 9 out of 12. And that makes sense when we look at this again, right? These 5, these 4. So 9 out of 12 are red or blue. However, we want neither red nor blue. So red or blue, and then we put that in parentheses not. Remember that thing here means complement, means all the things other than those, right? So red or blue, but we're looking for things that are not red or blue, so not those. And that can also be written like this. So not red and not blue. That means the same thing as this. Pause and think about that for a minute if you don't understand how these are connected. Just think about that for a moment. But the main thing is that is also 1 minus probability of red or blue, because all the possibilities minus the red or blue ones, we're left with the ones that are not red or blue. So again, 1 minus the 9 12s, which are the red or blue ones, gives us 3 12s, the remaining ones that are not red, not blue. And that makes sense. It is these 3 right here. In a Venn diagram, we have 12 ties in total. Here's our red ties. Here's our blue ties. We have 4 red ties, 5 blue ties, no overlap. There's no tie that's red and blue. And we have then 3 on the outside here that are not red, not blue. So those are our numbers there. And those numbers match what we've been doing here. And there's the 3 right here. Okay, again, pause if you need to and just take a look at everything. Those are ideas we've looked at, but it's important to distinguish between mutually exclusive and inclusive events. Okay, let's move on now to sample space diagrams. This problem here will kind of get us towards sample space diagrams. So let's take a look. It says in a group of 12 people, 1 person plays both archery and badminton, 2 people do only archery, and 7 people do badminton. So here's a Venn diagram. There are people that play both archery and badminton. So archery, badminton, how about you fill this in? What number goes here, 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 and then out here? So what are the 4 numbers that should fill these zones? All right, I hope you were able to come up with this. We have our 1 person playing both. We have our 2 people doing archery only, so that goes here. That means 3 people doing archery in total, and 7 people doing badminton, so 7 this whole circle, but there's 1 there, so that means 6 here. If you add those up, you have 9. That means 3 more out here that don't play badminton or archery. Okay, so with that, here's what we can draw to represent this. This is not a sample space diagram yet, but this is what's called a two-way table or contingency table. Two-way because there's basically 2 axes. We have this one and this one. So here's badminton and here's archery. And these are limited. They can only be related to 2 events like this, right? They're 2-dimensional. So here's the player that plays badminton and archery. So please fill in the rest of this table. What goes here, 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 all these spots. But the ones I'm going to ask you in the question is this one, this one, this one, this one, and this one. So what are those 5 numbers? Okay, let's check. Hopefully you came up with that. Double check your work. And now looking at this contingency table, we can answer a question like this, for example. Find the probability a person chosen at random only plays badminton. So what's your answer? Okay, on the Venn diagram, only plays badminton was these 6 here. And in the contingency table, only badminton would be not archery and badminton, which is a 6. So you can see that 6 and that 6 match. So this and this are the same thing, right? This is easier to see visually, but this is another way that you can be given data like this. So we have 6 out of 12, or 1/2. Badminton, intersection, not archery. Okay, next question. What is the probability of scoring less than 6 when two six-sided dice are rolled? To answer a question like this, sometimes it's easier if you begin with listing how many possible outcomes there are. This is a common situation, so you probably already know how many possible outcomes there are. But one way to represent all the outcomes is to consider a list of all the outcomes, and the best way to list that in this case is probably a sample space diagram. So one possible outcome, for example, is 3 on one die, 5 on the other, which we can represent as 3, 5, right? So a sample space diagram or probability space diagram could look like this. And I think, again, this is a common situation, this two dice thing. So you've probably seen this before. Here's one die, here's the other, all the possible rolls, and in the middle are all the possible rolls when you roll both of them. So here's our 3 and a 5, right? 3, 5, that's the score of 8. But the question here is, what's the probability of scoring less than 6? So imagine filling this, or fill that up and decide what's the probability of scoring less than 6. This sample space diagram will help with answering that question. Okay, so if you fill the table, there's all the possible rolls. Here's 1, 1, here's double 6, and everything in between. And our question, again, looking for less than 6, is only these ones here. So that's why a sample space diagram, in other words, finding some way to logically list all the possible outcomes, that's what a sample space diagram is helpful, because then we can see how many of the outcomes meet our condition. So here's the only ones that add up to less than 6. So that is 10 out of 36 possibilities, which can be reduced to 5/18. So again, that's a sample space diagram. It's often very helpful, unless, of course, your sample space is very, very big, and then you wouldn't want to list all the possibilities. Let's look at another example. We have a spinner with 1, 2, 3 on it. It's spun 3 times, and we're looking for the probability that the score on the last spin is greater than the scores on the first 2 spins. Could a Venn diagram and contingency table be used? Not really. Venn diagram, yes, but very, very tricky. Contingency table, no, because remember that's only 2-dimensional, and here we have 3 spins, so that already creates a 3-dimensional situation. So what are all the possible outcomes? Can you list them all? And then can you see which of all those outcomes lead to the condition it's asking about here? So try it out. What's the probability? So here's the answer. Here's all the outcomes. They're listed in a very strategic way here. There's 27 outcomes in total. And the blue ones highlighted here are the ones that meet the condition of the last spin being greater than the first 2 spins. So that's only 5 out of 27. Again, listing all the outcomes or making this sample space diagram was helpful in this case. Okay, here's another one. We have, so take a look, read that, and see if you can answer the question. And let's check our work. There's the sample space diagram. Here's highlighted the 2 options that meet this condition. Therefore, 2 out of 12 options, and then that's 1/6. Study that if you need to. And let's end this video by going back to our Monty Hall problem. As you may remember, the problem is there are 3 doors. You pick one, then the game show host reveals a goat behind one of the other 2, and then you have a choice to stick with your choice or switch to the other door because you're trying to win a car. All right, so here is something I want you to read. And I want you to take a look at this and see if you can fill the rest of this table. This table has been begun, but can you continue this table and put all the options? And once you've listed all the options, you can then answer how many ways are there for you to win if you stay with your choice, and how many ways are there for you to win if you switch from your original choice. So for example, you chose a 1, but the prize door is 3. So Monty shows you door 2 with a goat. And then if you stay with your 1, you will lose because the winning door was 3. But if you switch, you will win. So in that case, there's 1 win for a switch. And then another example, we have you choose 1, prize is behind number 2. So Monty shows you 3 with a goat. Then if you stay, again, you lose. But if you switch to door number 2, you win. So in both those cases, you won. Anyway, can you complete this table? So keep it going row by row until you have all the options and see what you get. And then see if you can answer what's the probability of you winning if you stay and if you winning if you switch. Okay, let's take a look. Here's the full table. So if you switch, okay, switch and win. 6 out of 9, you can see here 6 out of 9. Stay and win, only 1 out of 3 or 3 out of 9. Okay, let's take a look at this one in some more detail. I hope you're able to come up with this table because creating this kind of systematic approach to it, basically listing all the outcomes possible in the sample space, makes it much easier to see how this problem works. So again, here's contestant choosing door 1, 2, and door 3. And then the reason we have 3 times for each one is because based on their choice, 3 different things can happen, right? Because if the prize door can be any one of the 3 doors as well. So I hope the systematic approach there makes sense. Maybe you came up with something very similar. And let's look at then the probabilities then. So our original question when we did this Monty Hall problem was, well, is it better to stay with your choice originally or to switch the door you choose and do you have a better chance to win that way? And this one finally clearly kind of shows that it's better to switch. And again, if you look at the table, the way it's set up, when you choose a door and stay with your result, you only win 1, 2, 3 times out of 9. So again, when you stay and win, or stay, so the probability of staying and winning is only 3 out of the 9 options, which is a 1/3 chance. But the probability of switching and winning, switch then win, here you can see there's much more wins occurring there. So that's 6 out of 9 or 2/3. So much more likely to win if you switch. And it's always going to be in this proportion here, 1/3 to 2/3. Another way to visualize this is like this. I like this visual. It really shows what's going on. So let's say here are 3 doors, or in this case 3 cups, and instead of a car we have a diamond. So you as the contestant choose the correct cup. So you're pointing to that one. You don't know the diamond's there, but you're pointing there. So then the game show host reveals one of the other 2, and they say, okay, they're going to reveal that one has nothing, so we can say that choice has been eliminated. And now you decide to switch. And in this case, all right, you were already on the winning one, but by switching, you go to this one and you lose. So in that case, you lost. But that's only when you had originally selected the correct one. And now, and by the way, the chance you selected the correct one in the beginning is 1 out of 3, right? So remember that because that number is important here, right? Now, let's say instead, here's the 3 again, here's the diamond, but you chose the second cup. Well, if you're choosing the second cup, the game show host is definitely not going to reveal the diamond. They're going to reveal the other empty cup here. And so that choice is gone. So again, your finger's there, but we're saying that switch is often better. So we're going to, rather than remaining where you chose, you switch. In that case, you win. Third option is there's the three choices again. There was the diamond. You chose the third one now, which is also empty. So again, the game host has no choice but to show you the middle cup because they don't want to reveal the diamond is there. So they show you this one. That's now an eliminated choice, and you again choose to switch. And by switching there, you switch to the right one. So looking at these 3 scenarios, one time when you switched, you lost, because you had made the right choice in the beginning. But 2 times when you switched to the correct diamond. And again, so 2 out of 3 times you will win, 1 out of 3 you will lose. And the 1 out of 3 you will lose is only if you made the right choice in the beginning, which is 1/3 of the time. And then if you switch away, so that means 1/3 of the time by switching, you lose that win that you had, which was 1/3 of the time. So that makes sense. Switching loses 1/3 of the time, but wins 2/3 of the time. So great to come back to that problem. That problem's been following us for a few lessons. Nice to see it come together visually, and also using a sample space diagram. So you're now ready to try the assignment that follows this video. The assignment will have some problems on mutually exclusive events and also on sample space diagrams. Please practice before continuing to the next video, because it's important to build some confidence with the formulas and so on before moving on to the next topic.